So yesterday actually Gautam pointed out that the sequencing technique that I spoke about was not the only one in the market. In fact, there is another one that is slightly newer, which is called Nanopore Sequencing. Okay, so this actually does not rely on the polymerase, the DNA polymerase. It does not need the terminating triphosphates, right? You remember that chain that we had, P and 1 minus P. It does not rely on all that, but it does again borrow a lot of things from the normal biological machinery that you have in your body. Okay, so what it does is it has a very small pore, and we've seen this in Pranay's talks, right? You have pores in membranes, so they call this a nanopore. That's very tiny, which is, so there's a protein sitting there. I think it comes from some bacteria, and you have an enzyme, okay, that attaches itself to the purified DNA that you want to sequence, and comes and finds its pore, okay, the protein pore, and starts unwinding the DNA, and one strand, and only one strand, goes in, and the difference in potentials is measured by the instrument, which is different for every base. Okay, so this is what the ideal curve should look like, and now you will notice that there is no restriction on the length of the DNA molecule that you can sequence. Okay, so it can in fact do a whole bacterial genome, like 10 megabases or something like that. Okay. And the problem, of course, with this is that it still has more error rates than the DNA polymerase. The DNA polymerase is really accurate, okay, when it's copying. The number of mistakes it makes is very few, and which is what is exploited in the high throughput sequencing technologies. So here you are not using that, here you are using something else. Here it depends on how well you can measure the differences in the potentials that are generated because of the different bases that are going through. And if you have a long chain of A's, or C's or T's that are going through, sometimes deciphering that becomes a challenge. But the good thing is that it does not need one of those big sequencing machines. It is as big as your, it's as big as this, the machine that does it, and you can plug it into your, it has a USB port. You purify your sample, and then you just put a few drops on this surface, and then you plug it in, and there is hardly any alignment that is required, right? Because there's no, now you're not cutting it up and doing any, sorry, there's no assembly required, so it's very fast. Okay, so that's right now it's used to primarily detect bacteria. Okay, so if you have a lot of you have a sample of different bacteria and you want to know whether there is a pathogenic one in there, you can quickly figure it out. Okay, so right now it's used for that, but the technique is getting better, and hopefully better, and it's still a little expensive, but things will it looks like things will get better from here. You've seen Moore's law and everything, so things only seem to be getting better in the sequencing side of things. Okay. All right, so let's go back to a little bit about what we did yesterday, okay, at revision. So we looked at a very simple case of when you have to search a name, like your name maybe when you're searching in your list of to get your registration badges, right? You did a search to figure out where you were to sign there, and so if you write this in a computer, right, if you want to write a pseudocode, what will be the complexity, time taken? If you have number of students is n and you're looking for one person, what is the complexity? Order of n, right, because you have to look at every person in there, look at every name, match it with what the one you're looking for, and you go all the way till the end, right. And the worst case is kind of when you don't find your name, which is what happened to me. Okay, so I went all the way down, I couldn't find my name. So that was the worst case situation where I had to go through all n. There was, however, one thing. Those names outside, they were all sorted. Okay, you know what sorted means, right? They were alphabetically sorted. So if your first name I think by your first name. So if your first name starts with an A, you were on top, and if you had a Z in the beginning, you were at the end. Did you notice that in the sign up sheet? So can you do better than order of n in such a situation where you know that your list is sorted? You've done this as a child. You probably don't do it anymore, but you must have done it when they taught you how to use a dictionary. You had lots of words, you have lots of, you know what a dictionary is, right? A regular book dictionary. Did you use them when in school? Anybody who has not used a dictionary? Maybe in the last 10 years you've not, but at least in school, right? Yes, you have used it, right? So they're all alphabetically sorted, the words in there. So if you want to look up the meaning of a word, you don't really go through each page, do you? Because that will kind of take a long time. So what do you do? What would you do? Search for the alphabets. So if you're an A, if you know, if you're looking for the word mathematics, then you're going to look for A, then go to the B, C, D. But you kind of know that M is in the middle, right? So you're saying just look for the alphabet beginning, right? That makes sense. What if you don't know the language very well? Or what if there are arbitrary numbers? Okay. So did you understand what he said? So he's saying just go to the middle number, go to the middle page, see the name in there, the word in there. If your word lies after that word, then you just search in the second half of the book. If it lies in the first half, you check in the first half of the book. Make sense? And now what you've done is you had a big problem, a size n problem. Now you've got an n by 2 problem. Again here, you can continue doing that, right? Go to the center of the n by 2, check where you are. So for example, if your numbers, and they have to be sorted now, right? So let's do it with numbers, it's just easier to write. Okay, so let's say these are your numbers, and you're looking for the number 4. Okay, so what you do is go to the middle, which is somewhere here. You make a choice whether you go up or down. So let's say you choose the number 9, which is approximately middle. You see whether the number you're trying to look for, which is 4, whether it's less than 9 or bigger than 9. It's less than 9, right? So which means you need to search only in this half. You never need to look at this half of the list. Yes? Then you go and look at the middle of these, which turns out to be 4, so you're done. Okay, but let's say you were looking for the number 1. You would come here, you would look at 4, you would say that the 1 is smaller than 4, so let me look in the left side and go on doing that. Okay? So how much time do you think it takes to do this process? It should be better than n. Log n. Have you seen this before, this algorithm before? Do you know what it's called? It's kind of like bisection. It is bisection, yes, but it's called binary search. Okay, you're splitting into 2 pieces, and he claims that it takes log n. So let's try to see how why it takes log n. Okay, so let's say let's use the function t to describe the time in steps again taken for searching in a list of n numbers. Okay? So this is equal to, you first go to the center and do one comparison, right? So that's one comparison that you have to do. Okay? And then because of that comparison, you know which half to look into, right? So now you have a smaller problem of size n by 2. This still does not give you log n, but it kind of helps you understand the structure. Okay? So, what is this equal to? I can keep on writing this, right, because I know what T of n is. Right? So, this is equal to 1 plus, again I have to do a comparison, plus T of n by 4. Yeah? So, let us say I do this I times. So, what is my expression going to be? How many times do I get a 1? I times, right? So, I get a 1 I times, and what do I get here? This term becomes T of n by 2 raised to I. I do not kind of keep doing this, I stop when this term becomes 1, because once I get an array of size 1, I am done, right. I just have to do that one comparison, correct. So, when do I stop? When n by 2 raised to I becomes 1. Okay? So, that is my stopping condition. So, that is the and I is exactly the number of times you did this, right. So, what is I? If 2 raised to I is n, what is I? Log of n to the base 2, right. Okay. So, if I put this value of I in this expression, because I am trying to find out total what T of n is, right. I see that T of n becomes log n, right, because I just 1 comes I times, so which is I, which is log n, plus 1, which is order of log n. Okay. So, now from n searches, so if you had to do a million or let us say 1000 searches, you would now have to do only 10 instead of 1000. Okay, that is good, that is a good improvement, that is how log works. Right. So, here we found a better algorithm, but it needed this list to be sorted. So, if you want to do this many times, right, which is exactly the reason why this is sorted, the list is sorted out there, because you have all these people coming up and signing the sheet. So, it should be easy for the person to find, and this is going to, it should be easy for everyone to find, right, which is why you sort it beforehand. Okay, you pre-process your data, so that all subsequent searches become quicker. Okay, so, that is the goal of sorting when you know you have to do it many times, because sorting itself takes a little bit of time. If you are just going to do it once, then just an n complexity is good enough, okay, because sorting takes n log n, okay, which we are not going to talk about, but that is how much it takes. Okay. We did another example, which is power. Now, can you think of applying a similar concept to finding the power of x raised to n? Can you split it into small pieces? So, you can write this binary search algorithm very nicely as a recursive function. Do you know what a recursive function is? Anybody who does not know what a recursive function is? You just have to be honest, right? It will be hard otherwise, and it is okay to not know. Okay. So, we want to find x raised to n. Can you split it into small pieces, where each piece looks like the original one, but is smaller? So, you remember to do this, it took order of n. Okay, so, you want to do better than that. How would you split this? You know that n is an integer, right? 2. But the problem, yes, but the problem is n may not be 2 raised to I.
Means the summation of 2 to the power I plus 2 to the power I minus 1, which will make it n.
I am not sure I understand.
Suppose n is 7.
Yeah.
Then what will be the binary representation? It is 1 1 1.
Huh.
So 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0.
Yes, so you can, so you're saying that you want to represent n as is in binary, which is fine, but you have to find x raised to n.
Yeah, so we have split n in terms of 2 to the power n. So it will form a tree structure. I'm using the same concept.
Yes, that is good. That is good. Yes, you have to use a similar, and I think you're getting there, but you're looking at it from a different perspective because you saw I, 2 raised to I. It eventually does look like that. Okay, so let me give you a hint. If n is even, okay, take the case that n is even. Can you write this as two small, a combination of two small problems? Can you do something to n? N by 2, right? So, this is the same as x raised to n by 2 into x raised to n by 2, correct? So, if you want to find x raised to n, you can find x raised to n by 2. Do not call the function again, you know what it is, you square it, right. So, you are dividing it into two small problems. What happens if n is even, odd? What can you do? Correct. So, you can do even, 1, right. So, you can, if n is, this is if n is odd, sorry, even, and this is equal to like x raised to n minus 1 by 2 into x raised to n minus 1 by 2. So, you do this only once, right. So, you do not want to have a different number here, right. You do this and you multiply it by x, great. So, you can write a recursive function that does this. So, you call the same function based on whether your n is even or odd and then return the final answer. So, now what is the time complexity of this? What do you think it's going to be? It's again going to be log n, because to compute this, if it takes t of n time, right, in the even case, it is going to take t of n by 2. You do not call it again, you called it once, you have the answer. Okay? So, that is important, because if you do call it again, this becomes 2 times and then your complexity gets screwed. Okay? So, you have to do t of n by 2 plus 1, right, the multiplication. In the odd case, it is t of n by 2 plus 2 at the most, because this actually it's n minus 1 by 2 too, right. So, it's, you can say this is at less than or equal to t of n by 2 plus some constant. If you solve this, you will again get c times log of n as your complexity. C is a constant, so it becomes order log n. Okay, so, these methods, these two problems were solved with a problem called divide and conquer. Okay. So, you are dividing into smaller pieces, chunks of problems and of similar problems, okay, and then solving them and then putting them back together. Okay. So, that is a technique of designing an algorithm. We saw the cashier problem yesterday, okay, which I said was an instance of a greedy approach. Okay. So, let us just take a look at that. So, let us say you have denominations of 1, 5, 10, 20 also we have, right, 20, 50, 100, let us stop here. Okay. These are the denominators, actually you just have one more that the cashier would need to give change. Okay. So, the cashier, let us say, has infinite supply of all these notes, and you come up, pay for something with a bigger note than what is required, and the cashier has to make change and give it to you. So, if the change is that the cashier has to give is 251, he is going to, he or she is going to take 200 rupee notes, 150 note and 1 note, correct? That seems, that is the most reasonable way when you are optimizing for the number of, minimizing the number of notes. Okay, and this actually works in our system. Okay, so this is a greedy approach. So the greedy approach is saying you want to minimize the node, so give the biggest node that you can give, then reduce the problem to a smaller problem of a similar nature. So when you took, first give a 100 node, okay, so minus 100. So now you are left with having to give 150. Again give the highest node. So now you have to give 50, sorry 1. Now give the highest node possible, which is 50, right. Now you are left with 1, so give 1. Okay, so that's the greedy method of giving back change. Now would this work for all denominations? This is called denomination, okay, of nodes. Can you think of, well, the answer is no, it doesn't. Okay, it works for us and it works for most national currencies, but it need not work for arbitrary denominations. So you, as an exercise, think of a set of numbers where this technique of giving away the biggest nodes first actually gives you a lesser, sorry, actually gives you a worse answer than the optimal. Okay, so greedy methods don't always work. Sometimes, in fact, you can prove that it works for this, but it's hard to do that. Okay, so sometimes they're provably correct, sometimes they're not, but they work in practice. Okay, tomorrow I'm going to ask you for the denomination where this does not work. Okay.
If I get a number whose remainder by 10 is not any one of them, then will it work?
If you get a number like this, what is the number?
Sir, 253.
253, yeah.
So if I get the remainder divided by 10, then it will not appear in this 1510 or 500 or
No, so there is no division, so you are only subtracting, right?
yeah, then you cannot return 253 rupees using this denomination.
Why not? You give 3 of.
You get 3 1 rupees.
Yes, 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 you can take as many and you have to have 1 in your set, otherwise it is not an answer, you can't even solve the problem in this case. So for an arbitrary change, to be able to give the arbitrary change, you need to have enough 1s in your set. Okay, but I mean you can always give 251 ones, but that's a terrible idea. Okay, so you have to think. Tomorrow I have 2 classes, so one of these classes we are going to discuss denominations. Okay, so it might be useful for you to figure out one way to where it's not, it doesn't work. Okay, the other thing we discussed was the matrix chain multiplication. Okay, and I said that exercise at home, I mean in the hostel. Yes. Okay, so you have A1, A2 up to AN, right, n matrices, and you want to find the best way of parenthesizing them. And we said that if P of n is the total number of ways you can parenthesize this big chain, then you can write this as the sum over k going from 1 to n minus 1 of P of k into P of n minus k. Correct? The rationale was, let us just look at the last multiplication that we do. Okay, so let us say we do it after the second matrix, which means you multiply everything on the left, multiply everything on the right. The ways of multiplying on the left is P of k, right, if you have split at k. The ways you multiply on the right is P of n minus k, right, and you can choose your k, right, wherever. So you have all these options, you can do it after 1, 2, all the way to n minus 1. Right, so that's how you get your summation, and this grows exponentially. Okay, in fact, this is greater than 2 raised to n. Okay, this grows like that. So now let's, how do you solve this problem? We just said that there are many combinations that you would have to go through if you did it in this naive way to figure out the best way to multiply them. Okay, so now let's look at a technique that will do this much faster than 2 raised to n. So first we need to define the problem. Okay. So let matrix AI have dimensions pi minus 1 by pi. Okay, so which means my matrix A1 will have dimensions p0 by p1, right. My matrix A2, my number of rows need to be equal to the number of columns, right, which is why this I minus 1 comes up, will be p1 by p2, right, and my an is going to have dimensions pn minus 1 by pn. So essentially I have a set of numbers from p0 through pn, that is my input, right. Remember, I am not trying to find the number of parenthesizations, I am trying to find the best parenthesization where the number of multiplications is the minimum, is the least, correct. That is the idea, that is the question we are trying to solve. All right. So, suppose somebody tells us beforehand, right, that the split is going to happen after k, the final split that we use to compute the number of parenthesizations. Let us say somebody tells us it is going to happen after the kth thing, okay, which means now you have a hint now, right. You have been told that you multiply A1 through AK first, then you multiply AK plus 1 to AN. I mean, this you can do in any order, you can do this first or this second, but you do the final multiplication at the very end. Let us say somebody told you that, okay, that is like a hint they have given you. So, what does it say about this multiplication? So, I am going to argue that the best way to multiply these numbers, these matrices, there is some best way of multiplying these matrices, correct? You agree? There is some way of parenthesizing this A1 to AK, which is the optimal for this problem. This problem is very similar to our big problem. It is just a small set of smaller set. So, the optimal way of multiplying these matrices is going to be part of the bigger solution. So, if you were just given this problem, small problem, right, on the left, A1 through AK, and asked to solve that, whatever solution you get is going to be part of the bigger solution. Does that make sense? This is like telling, let us say you have a graph, okay, of connections, you want to go from point A to B, somebody tells you that the best path goes through C, okay, there is no direct best way to go through A, you go through C. Then the solution to go to C, the best solution to go to the smaller problem, the A to C, is going to be part of the bigger problem, right, because if you could go in another way, if you could do this in a better way, then that will still be part of the bigger problem solution. Does that make sense? So, there is a substructure in this problem, okay, which we are going to exploit. Okay. So, let us say I have a variable m I comma j, which stores the minimum number of let us say the number of multiplications, or you can say the cost of multiplying for finding AI to AJ. So, let us use m to store the cost of the optimal solution for multiplying AI to AJ. So, mi comma j is AI to AJ. Okay, what do we want to find? M of, what is our goal? To find M of 1 comma n, right? That is what we need to find. Okay, that is what we need to find. I am defining an arbitrary I and j, where of course I has to be less than j or equal to. Okay, you are so far with me. All right. Now, again using the same logic, somebody tells me that a k in between I and j is the best solution. Okay, that is where you have to split it. So, I can write M of I comma j just get a bigger chalk. To be equal to, okay, so now I have split between I and AI and AJ, right. I have some k, AK, at which I am multiplying, right, stopping the multiplication. So, this is going to be the optimal solution from I to k, correct. Those are the number of multiplications you have to make, right. You also have to do the second part from k plus 1 to j, right. So, you have to do those, and you have to multiply these two. So, how many multiplications do you need for that? There is another term, right. So, now what we've broken the problem as AI to AK, we are multiplying, right, which is this, that is the cost of multiplying those matrices. We have AK plus 1 to AJ, which is this cost, and now we have to multiply these two. Now, I have one matrix. What is the size of this matrix after multiplication? P of I minus 1, no, P of I, right, P of I by, P of I minus 1 by Pk, right, that is the size of this matrix, correct. What is the size of this matrix? Pk by Aj, right. Pj, thank you, good. So, these are the matrix sizes, right, and how much does it cost to multiply matrices of this these dimensions? PQR, right. So, how much is that? Pi minus 1, Pk, Pj. Okay, so, we have got some sort of a recursive solution now, right. It is made up of smaller pieces, except there is a catch here, we do not know the k, right, we do not know which k to use. I said that you know, if you know the k, then you can do this. But how many possible k's are there in this case? From I to j, right. So, you can just look at all the k's and take the minimum, because the whole point is to minimize the cost, to minimize the number of multiplications. So, you minimize this quantity over all k going from I to j. Does that make sense? You should stop me and ask, because we are going to use this technique, although it does not look like biology, this technique of breaking into little pieces a lot. Okay? Does that make sense? Because you are minimizing, no, finally. So, this solution has to be the best solution of a bigger problem also, and it is made up of smaller problems, and the solution of the whole thing has to be the minimum, correct. So, we can just find this value by looking at the smaller piece, filling up the smaller pieces, doing this additional term, adding this additional term, and minimizing over all k. Okay. So how do you do this in practice? Okay. So so M is a matrix, right, of size, I mean it is a 2-dimensional array. I can go from 0 to n or n minus 1, and j can go from 1 to n, correct. So let me just draw my matrix. This is M, okay. There are lots of matrices in here. So this is the matrix for the solution, okay, which we are going to fill up, okay. So here's my one, there's my I, right, here's my j, 1, 2, right, all, wait, n, n. And we decided, we've established that our solution lies here. M of 1 comma n is where the best solution is. Yes? I see some lost spaces, you have to stop me right then when you think that something is not making sense. There are some numbers in this matrix that are that are undefined, which are what? What happens when I is bigger than j? You cannot multiply, correct. So we don't really care about things that lie below, right, those are, that's not defined in our system. What about M of I comma I? No multiplications, right, so 0. So we know those numbers also, so we can fill up those numbers, right. Okay, we cannot fill up this guy directly because it depends on things that we don't know the values for, right, but we can fill up the smaller numbers first. So think about 1 comma 2, okay. What does 1 comma 2 depend on? So I is 1, j is 2. Okay, we are actually multiplying just two matrices, A1 and A2. Okay, so my k I have to split, there is only one way to split really, which is after A1. Okay, so that is going to be M of 1 comma 1, which is 0. Okay, M of 2 comma 2, which is also 0, plus P1, P0, P1, P2. Which is reasonable, right? You are just multiplying two matrices A1 and A2 and you have no option but to do it this way. So you can get this number by looking at these two guys. Okay? So let's just do the same problem that we did yesterday. So I think we had 10,000 by 2, 2 by 2. And I think it was a 2 by 4, but let's keep it small. Okay, let's make this, because I have to do the computation. So 10 by 2, 2 by 2 and 2 by 2. Okay, these are our three matrices. So this is my P0, this is my P1, P1, P2, P2 and P3. Okay, so we are multiplying three matrices A1, A2, A3. Okay, and we want to find the best way of doing the multiplication. So our matrix has to be of size 1 by 3, right? So I don't care about these lower triangle ones. I know this is all 0. Yeah? And this is 1, 2, 1, 2 and 3. Okay, so now let's do M of 1 comma 2. So my k can only be 1, okay, which means I add M of 0 comma 0, 1 comma 1, which is a 0, to a 0, and these numbers, which is P0, P1, P2, which is 40. Yeah, good. I can't do this one yet, okay, because it depends on this number. Okay, so let's do this number first. This is multiplying, this is doing m of 2 comma 3. Okay, so m of 2 comma 3, again my k can only be 2. Okay, there is no option. So it becomes 0 plus 0 plus multiplying these two matrices. So that's just 4 or 8. 8. Okay, now comes, at least you know there is some use of that minimum function. Okay, let's do m of 1 comma 3, which is the final answer. So my k can be 1 or 2. Okay, so what happens if k is 1? Then m of 1 comma 1 is 0, right? M of 2 comma 3 is 8, right? So I have to take that into account, plus what is this value? P0 10 into Pk is 1, so 2, 10 into 2 20 into 2 40, yes? Okay. So this becomes 48. What happens when k is 2? I have to multiply, I have to add 1 comma 2, which is 40, right, plus 2 comma 2, which is 0. So I have to do 40 plus, I have to multiply again 10, 2 Pk is 2 and 2 again, right, 40, right. So I have to choose between 48 and 80. What should I choose? 48, the minimum one, right. So that's how we got the solution. Okay. So you'll notice that the way to fill this matrix is like this, because those are the values that you have at any point, the diagonal ones. Okay. Does this tell you how to parenthesize? This just tell you the minimum number of multiplications needed, which is 48. It doesn't really tell you how to parenthesize, does it? Do you understand what I am saying? This has just told me that the minimum number of multiplications required to multiply A1 through A3 is 48. But it still does not tell me whether I should multiply A1, A2 first or A2, A3 first. How can I get that information? So the way to get that is, it's a trick. Okay. Whenever you choose which k you used, you just remember it, you keep a pointer. Okay. So in this situation, okay, you chose a k that was 1, right. So just remember that the k that you chose was 1. The k that you chose here, you had no choice but to choose a 1, right, or 2, a 1, yeah, and this was a 2. Correct? That was the k you chose to get there. Okay, so this is like a clue that you are leaving at every cell, whether that cell is used or not, you just remember how you got there. So for any solution that you compute, you just record which k, you be the oracle that I spoke about. Let us say somebody tells you what the k is. You actually do know because you found the minimum k. So keep it, store it somewhere. So now once you know the answer, right, you can go to that k. So that k will tell you the final two matrices that you have to multiply. So this one tells us that the final split has to be after A1, which means the next split has to be between, you have to figure out how you split the left part and the right part in a recursive way, because you have that. So you go to 2, 3, you have all those pieces stored. So, you notice that when you go to 2, 3, it tells you that split at 2, which is trivial in this case because we have taken a very small example. 4 matrices would have been ideal, but in this situation this is the 2. So, it tells you to split here. A1 there is nothing to split, so you are done. Okay, so, it tells you the way to parenthesize if you remember a little more information. Okay, what is the time complexity of filling up this matrix? You have done this before. Tell me the time complexity. That is the dimension of the matrix, yes. For every cell, how many computations do you have to make? So, he is saying that the dimension, it has to be at least n square, yes, because you are filling up the upper half, right, which is n square by 2. Okay. We do not care about the constants, no? So, it is n square so far, but for every cell, to compute every cell, you are not making constant number of computations, because you have to find the minimum. It ends up being n cubed totally, because the number of computations is approximately n to find the. So, when you are doing this guy, you have to find the minimum between this plus this plus this, and there is going to be more. Okay. For the next guy, you are going to do n minus 1. For this diagonal, you do n minus 1. As you go closer and closer, you do fewer things, but you get a series which I am sure you know how to sum, 1 plus 2 plus 3 up to n minus 1. Okay, and you have a total of n square things to fill up. So, you get a complexity of theta of n cube in this case, which is much better than doing a parenthesization. Agree? I mean, doing all the parenthesizations. So, look, go back home and not home, the hostel, so, and try to do this for 4 matrices. Okay, it's good exercise and see what you get. Because for 4 you can also do the brute force method and see all the combinations. All right, this what I just spoke about is called dynamic programming. Okay. The word programming is not associated with the coding kind of programming. Okay. So, many years ago a program really meant a table. Okay. So, here what you are doing is essentially filling a table, that is the programming word comes from that. Okay. So, all dynamic programming methods usually have some table to fill up, where the final answer depends on little pieces that are present in the table that you have calculated earlier, okay, during the process. Okay. Shall we move on to biology? All right. So, we are going to talk about sequence alignment. Okay. So, this is a problem of comparing 2 biological sequences for now, okay, and to find similarities between them. And the similarity is a function that allows insertions in one or the second sequence, deletions in some sequences, and substitutions. Okay, I'll tell you what they are. The question is, why should we do this? Do you have any idea why? We've seen the genome, right? We've seen yesterday the genome sequencing, the assembly. Now we're talking about how do you compare? Why should you want a way of comparing 2 biological sequences? One reason is to see how evolution has worked. Okay, so if you have a genome sequence of the human and a monkey, you can do a sequence alignment, okay, and see how similar they are. Okay, and that will give you a sense of when or how the evolution happened. You can also compare with mouse or whatever, right. The other reason is you might get a new protein that you have sequenced. You might have a sequence of a protein and you want to see out of all the known proteins, we have lots of proteins, right, that have already been sequenced. We also have structure, but let's just look at sequence. We want to know what this protein does. Okay, this is a novel protein that I have just sequenced. I want to know what it does. So, one way of doing it, one way of figuring out what it does is to use prior knowledge, which are all these proteins that have already been sequenced, been characterized. Can I compare with each one, right, and see which one it is closest to? That will give me an idea about what that protein does. Okay, so, that is the other motivation behind doing sequence alignment. Okay. So, when I said insertions, deletions, substitutions, it is because mutations work kind of that way. Okay. So, let us say you have your original DNA sequence. Sometimes, very rarely though, the DNA polymerase makes a mistake. Okay. It can substitute, instead of a C, it can substitute an A or a T, okay, during the and somehow the proofreading process does not work, and you get a mutated sequence. This can also happen because of UV radiations or other environmental factors where your DNA can change. The other change that can happen is a deletion. Okay, so, here you notice that the CG, that second CG is just cut out, okay, or you might have an insertion. Okay, this can also happen when the RNA polymerase is reading something and then temporarily slips, goes back to something it has already read and continues. Okay, so, that can also happen. It is rare, but it can happen. Okay. So, keeping these insertions, deletions in mind, people have done these kind of pairwise alignments. Okay. So, this is the human with the rhesus monkey, and you can see here this is the genome browser again. You can also observe lots of things on that browser, where you can see that there are a few mutations here. By mutations, we are not saying that during copying A got mutated into a G, we are just saying that the common ancestor had something else, okay, in there, either an A or a G possibly. But whatever, all we really can tell from this is that the monkey has a G there instead of an A. Okay. The mouse, if you align, you see more changes, because the mouse is, as you can imagine, further away from us than the monkey is, right, and you will see some deletions come up. This is a random piece of DNA. Okay. This is, you can look at genes. If you have a favorite gene, you can go and look at it. Okay. So, how do we do this in the class? Okay. So, let us say you have these two sequences. How do we align them? Thank you. First of all, how many ways do you think are there to align? It's not a trivial answer. So, but what do you think? How many do you think it is? Let me do one alignment, which to me makes the most sense. So, here I have put an insertion, okay, so that I can do something to that T. So, that T gets a partner. If I do not have an insertion, right, my T will align with a G and my G will align with a C and so on. But this way, does that seem okay? Does it seem like a reasonable alignment? Have I made a mistake? So, see, there is a perfect match between the other letters except this guy, right. Here there is a mismatch. Okay. So, that is one way of aligning. Okay. There are many ways of aligning two sequences. If you have a sequence of length m here, and a length n here, there are at least m plus n choose n ways when you have gaps in there. There are at least, there are actually more than that. Okay, so this ends up again being, you know, an intractable problem. So it's an exponentially growing problem. But we have still not, these are just the number of alignments. What is a good alignment? We need to have a measure of a good alignment. So in the matrix multiplication, we knew exactly what we wanted. We wanted minimum number of multiplications, right? We still haven't, you know, in biology it's all, you have to also frame the question correctly, okay, and then you can worry about solving it. So one way is to treat every the distance or the similarity between two nucleotides, okay, and store them as a similarity score or similarity matrix. Okay, so here what you're saying is that whenever an A matches with an A, you give it a score of 1. Okay, whenever there is a mismatch, okay, between a nucleotide and another nucleotide, give it a -1. Okay, so penalize it. And whenever you have to introduce a gap, that is a worse thing to do. Okay, so let us give it 2, -2 penalty. Okay, sounds a little ad hoc, but you know that's what we come up with. We've come up with. Okay, so let's say that is our matrix. Okay, what then is the score of this one? So C matches with a C, right? So you get a 1 plus 1 minus 2 plus 1 plus 1 plus 1 plus 1 minus 1 plus 1 plus 1 plus 1. Okay, so we are assuming that these scores, these columns, the mismatch or the match, the similarity score of the columns can be added, and the addition of all these similarity scores is the answer of the similarity of the is the similarity score of the complete alignment. Okay, so we are saying that it's additive. Okay, so in this case it is 1, 2, 3, 4, 5, 6. The score is 6. Yeah. Okay. So that's how we are going to define an alignment, multiple alignment problem. So now, if you look at the m plus n choose n, this is again I think greater again than 2 raised to n. Okay, again this is a massive problem. Okay, if you have m, this is assuming that m is the same length of n, it becomes 2n choose n, right, which is really big, which apparently looks like that, okay, with some approximations. So going through each and every thing is cumbersome, okay, but we can use the dynamic programming trick if we can identify subproblems, okay, in this big problem. Okay, so let's be more specific. So you have two sequences, x and y. X is x1 through xm, little x1 through xm. These are all nucleotides for now. So size m, size n. And when you are doing these alignments, you are only going to look at mutations, insertions, deletions. You are not looking at shuffling. Okay? You are not allowing that. So you can't say that, you know, maybe I can switch these around and get a better match. You are not allowing that. So the output then is a list of columns. Okay? So where every x, little x comes up somewhere and every little y comes up somewhere. Okay? So every xi is either in alignment with a yj or with a gap. Similarly, every yj is aligning with some xi or with a gap. Okay? All right, and you want to find such columns with the highest score. And it should, when you find the columns, you have to make sure that the sequences don't get shuffled. So that's obvious. So how then do we spot the substructure in the problem. Let's only deal with prefixes of the problem. Okay. So, everybody knows what a prefix is. Prefix is of a string, starts from the beginning of the string and ends somewhere in the middle or at the end. Okay, that is the first part. Suffix of a string is the opposite. So, it starts somewhere in the middle, but it definitely ends at the end, that is the end. So, we just look at the prefix. So, instead of solving the big problem, let us see if we can solve smaller problems, where we are trying to align the first I characters of x with the first j characters of y. Okay. Look at the original problem. Okay. So, let us see if we can, with the original problem, identify the substructure quicker. Okay. Now, there are three possibilities with the last letters, right? Either xm matches with yn, or xm matches with a gap, right? That is a gap, the hyphen, or the yn matches with a gap. These are the only three possibilities. Right. Now, what if xm matches with a yn? What does it tell us about this part of the problem? What does it tell us about x1 through xm minus 1 and y1 through ym minus 1? Yes. No, it need not, but suppose it does. Suppose like k, right? Somebody told you that k is where the split happens. Now, somebody is telling you that the last two characters are definitely going to match in the optimal solution, if you are told by some oracle. Then what does it tell you? That is like a hint. What does it tell you about the rest of the problem? The value of what? Those, correct. That value will be?
Less than m minus
1. Yes, that is correct. That is true. But what else? That is true, that is what it tells us, yes. It does not exactly help with the substructure problem, but is there anything else that you can say about the optimal solution for this problem? Is the optimal solution for this problem going to be part of the bigger problem or not? So, if we can solve this one, we just have to add xm and yn and then we are done. Okay. This is the same thing as saying that you go through this neighborhood for the shortest distance, then you know that going to that shortest distance, the optimal answer for this best way of aligning these two sequences is going to be part of the best way of aligning the whole thing, because xm is matching with yn. Okay. Yes. So, that means if my let me store in my V, again a matrix, the similarity value, okay, so best score of the two prefixes ending in I and Y, I and J. Okay. So, what is in this situation, what is my V of m comma n, that is the final answer, right, that I need, is equal to the value of this guy, right, which is what? M minus 1 comma n minus 1 plus the score of matching these two, right, which let us say we use a matrix S for that, x of x xm comma yn, correct. But that is only if you're matching xm with yn. What if you're not? What if you are doing this situation where your xm is matching with a dash? What then does that mean? That means your yn is shifted, exactly, right. So, now my optimal solution is contains x1 through xm minus 1, y1 through yn, right, and then a gap, right. So, it is either this or it is v of m minus 1 comma n, right, plus the gap. So, let us just say the g, okay. Let us call the penalty g, okay. And the other alternative is when your xm is here and your yn is matching with a gap. That is the very end, right. What is the solution? M comma n minus 1 plus g. This is like your penalty. Okay, so that is your recursive definition. So, technically instead of m and n, we should have I and j, because you want to do it for all I, because again this guy, the same concept will stay, right, because now this is out of the picture in this situation. We only have to solve this smaller problem. Again there we have 3 cases where xm minus 1 matches with yn minus 1 or with a dash, or the other guy matches with a dash. Each time we have 3 options. Okay, so, how do we fill up this matrix, the matrix V? What is the size of the matrix V? M by n, right. We will add an extra row and a column for 0th. Okay. So, what does V of 0 comma I mean, sorry 0 comma j mean? It means that you are not looking at any of the x, right. You have looked at the first j characters of y, right. This is for the first characters, and this is the similarity value of nothing with Vj x y1 to yj, which means all of them are mapped to a gap. Does that make sense? If you map all of them with a gap, what is this value going to be? J times g. Our g is negative, okay, so it is going to be a negative number. Does that make sense? What about the reverse situation? V of I comma 0 is going to be I times g, right, and 0 comma 0 is 0, it is like nothing there. Okay, so, now what we have is the first column and the first row, which we can fill up. So, let us do that. Let us take a smaller example. I do not want to take that massive first thing, that we will leave for your tutorial tomorrow. So, let us say my x is AC and my y is AGC. Okay. Do you guys remember the I erased the expression. Okay, let me write the expression and then minimum over the 3 quantities. Okay, so my matrix is going to be of size 4 by 3 with a 0 added. So 5 by this is going to be 4. Okay, so this is a 0. Let's go to our this is our similarity matrix. Okay. So what is this number going to be? -2, right? -4 and -6, right? So this is index 1, 2, 3. This is index 0, 1, 2, 3, 4. Okay, you have to stop me if something is not clear. You can. Okay. -4, because this is the second character, right? So you have actually put 2 times G. G is -2, right? Because you're putting 2 gaps, right? Here you're putting 3 gaps. Again, here this is going to be -2, -4, -6, -8. Right? Okay. All right. So here we cannot really get away with filling only the top half or the bottom half, right? We have to fill up the whole matrix. It's not like the matrix multiplication. So each dynamic programming algorithm will be different. The concept is all that you have to get. Okay. All right. So what is the order of filling? Where is our solution in this? It's over here, right? Our solution lies here, which we have to fill up. What does any arbitrary box depend on? It depends on the diagonal above, right? Diagonally above one block, and left, right, and top. So it depends on these 3. Every box depends on what's on its left, what's on its top, and what's on the diagonal on this side. Okay. So we cannot fill this guy clearly. So we can fill up either row wise or column wise. So let's do that. So the first thing that we have to fill up is this one, which is V of 1, 1. Okay. So this is 1, 2, 3, 4, 1, 2, 3, right. So V of 1, 1. Okay. So it's either V of 0, 0 plus the cost of matching it, right, or you go left, right, you go up, right, go I minus 1, so extend the gap and don't match it, right, or you extend this bottom, this guy's gap and don't match it, okay. So -2 plus -2 is -4, this is also -4, so both these things are really not very good options. This option is 0 plus 1, right. So the minimum in all this, the maximum, you should tell me if you notice some mistake, there has to be a maximum there. Minimum for matrices, maximum here, right, because you are looking at similarity, not distance. You can just reverse the sign and make it max. So this is 0 plus 1 or -4 or -4. So it has to be a 1, right. So we can fill row wise. What is here? What happens here? So we can either align G with A directly. That means it is -2 plus -1. Right? Let's write it down because. So we are trying to solve V of 1, 2. Okay, which is either First option, V of 1 comma 1 plus matching 1 comma 2. What is matching 1 comma 2? Matching A and G is a minus 1 because they are not the same. And what is V of 0 comma 1 is a minus 2. So, it is a minus 3. The first option is minus 3, correct? This is minus 2, minus 1 is minus 3. The second option is when you are not matching the two, instead you are putting a gap. Okay? This is V of 0 comma 2 plus, you have to put the gap, right. So, minus 2. What is this equal to? 0 comma 2 is minus 4 minus 6, correct. Okay. The third option is V of 1 comma 1 minus 2. Is 1 comma 1 is this one, right. So, 1 minus 2 is minus 3, no minus 1. Okay. So, see, that was on purpose to make sure you were paying attention. Okay. So, that is a minus 1 then, right. I have to take the maximum. The maximum of these 3 numbers according to me is minus 1. Okay. All right. That okay? What happens here? Figure it out and tell me the number. I will take your word for it. Do not look here. So, I had a cheat sheet, so I knew the answer. I think if 7 of your numbers match with the 10 here, you are okay. Check if at least you are approximately close, or take your time. Okay, I have just 5 minutes, so let's move on. We will do a bigger problem tomorrow. Okay, so if you have calculators and if you want to take help of a computer to code, you are most welcome to bring it, but a calculator might also suffice. Okay. All right, so this is what you are supposed to get if you follow this recipe, okay, which means that your the best way of aligning has a score of -1. Does it tell you the best way of aligning? Not really, it just tells you the best score, I mean the score of the best alignment. So, this is the same thing as with the matrix multiplication, right. We were each time calculating only the cost, the best, the minimum cost or the maximum similarity, right. We do not know the way to get, so we need to construct the alignment from here. Okay. So, again when you are computing this matrix, you can remember a few things, right. What should you remember as you are calculating this, any matrix? Yes. So, you remember how you got there, right. So, we took one of the 3 options, right. So, what you should do is when you are writing the numbers, whichever way you came from, you either came from here, okay. If you are using this, you came from top, right, or you came from the left. And what does this really tell you when you are coming from top? It is just telling you that you have to put a gap. If you are coming from the diagonal, it is telling you to match it, it is telling you exactly what to do, right. So, in this case, this is what the arrows look like. So, this -1 comes from taking this match A and G, whatever you get for here, and extending it and putting the 2 C's together. Okay. So, it must have been a -2 plus 1, which must have given a -1 here. Okay. So, you just remember that. Sometimes there is a tie, okay. There are 2 ways that you can get there. So, you can choose to remember both if you like, right. So, I will just, and you do not do it only for the last one, right, you have to do it for all, because you do not know which square is going to be used in the final answer, right. So, this is there are just too many arrows, I will do this tomorrow. So, instead let us do this other quick thing. What is the time complexity? Forget the arrows, tell me the time complexity of getting this number. O of what? Now your answer n square. Okay. This is not like matrix multiplication, because you did not have to find the minimum or the maximum over a range of numbers which were growing. What you are doing here is you are always relying only on a constant number of comparisons. You are either going up, you are coming from up, left or diagonal, right. That is all you are looking at. So, for every computation, every block, you only have to make 3 comparisons and a few additions, right. That is again constant. Let us say 3 additions and 3 comparisons. Okay, it is constant. So, to get here, you have to fill up the whole, all the boxes. So, you have to fill up n into m boxes, right, and every box takes a constant number, which we do not care about in this class. So, it is the way to find the optimal optimal alignment takes order of mn time. Okay. Now, when you are dealing with genomic sequences, you have to also worry about space. Okay. So, how much space are you taking? It is also mn, right, because you need to have this whole matrix, right. Do you need to have the whole matrix? At any point in time, when we were going row by row, right, did we worry about what happened 2 rows before? Every number depended on the number on its left and the top row, let us say, right. So, at a time you in memory you only need to store the row before it and your current row, right. You just have to store 2 rows at any point in time to find the best. You do not really need to store the whole matrix, because when you did this, when hopefully you found this number, when you found this number you did not really care about these guys, they were all used and there is no need for them. Okay. So, you can in principle find this number -1 in linear space, okay. Linear in terms of, now which one, you could have also chosen a column, you could have filled it column wise, right. So, what should you choose? Should you do it column wise or should you do it row wise? If you do it column wise, you need to store the previous column and your current column, you need to store 2 columns. If you do it row wise, you need to store 2 rows. So, you can look at the sizes, right, you can see what is bigger, is m bigger or is n bigger. If m, in this case m is bigger, so it is better to store the rows, because you have to store fewer rows. So, you can take a call based on the size of the sequence and decide how much space to use. Okay, we will stop here. If you have questions about this, you can ask me now or you can ask me tomorrow also. We are going to do more of dynamic programming tomorrow. And, yeah.
So the backtracking pointer seems to be.
Good point. So, we will do this tomorrow. Yes. So, he is pointing out, rightly so, that the pointers that we have to trace back, you need all of them. So, this linear space currently, what I have told you, only works for getting this, but tomorrow we will see how to do the backtracking also in linear space. Yeah. Okay. Thank you.